Continuous particulate air monitors, CPAMs, have been used for years in nuclear facilities to assess airborne particulate radioactivity, APR. In more recent times, they may also be used to monitor people in their homes for the presence of man-made radioactivity. These monitors can be used to trigger alarms, indicating to personnel that they should evacuate an area. This article will focus on CPAM use in nuclear power plants, as opposed to other nuclear fuel cycle facilities, or laboratories, or public safety applications. In nuclear power plants, CPAMs are used for measuring releases of APR from the facility, monitoring levels of APR for protection of plant personnel, monitoring the air in the reactor containment structure to detect leakage from the reactor systems, and to control ventilation fans when the APR level has exceeded a defined threshold in the ventilation system. CPAMs use a pump to draw air through a filter medium to collect airborne particulate matter that carries very small particles of radioactive material. The air itself is not radioactive. The particulate radioactive material might be natural, example radon-decay products, progeny, example 212Pb, or man-made, usually fission or activation products, example 137CS, or a combination of both. There are also gas monitors which pass the air through a sample chamber volume which is viewed continuously by a radiation detector. Radionuclides that occur in the gaseous form, example 85Kr, are not collected on the CPAM filter to any appreciable extent, so that a separate monitoring system is needed to assess these nuclide concentrations in the sampled air. These gas monitors are often placed downstream of a CPAM so that any particulate matter in the sampled air is collected by the CPAM and thus will not contaminate the gas monitor's sample chamber. In monitoring, the region of deposition of this material onto the filter medium is continuously viewed by a radiation detector, concurrent with the collection. This is as opposed to a sampling system, in which the airborne material is collected by pumping air, usually at a much higher volumetric flow rate than a CPAM, through a collection medium for some period of time, but there is no continuous radiation detection. The filter medium is removed periodically from the sampler and taken to a separate radiation detection system for analysis. In general, sampling has better detection sensitivity for low levels of airborne radioactivity, due to the much larger total volume of air passing through the filter medium over the sampling interval, which may be on the order of hours, and also due to the more sophisticated forms of quantitative analysis available once the filter medium is removed from the sampler. On the other hand, monitoring with CPAMs provides nearly real-time airborne radioactivity level indication. It is common practice to refer to sampled air even when discussing a CPAM, i.e., as opposed to monitored air, which would, strictly, be more correct. There are two major types of CPAMs, fixed filter and moving filter. In the former, the filter medium does not move while the airborne material is collected. The latter type has two main variants, the rectangular deposition area, window, and the circular window. In both types of CPAM, the sampled air is pulled, not pushed, by a pump through the piping of the monitor up to the structure that holds the filter medium. It is important to note that CPAM pumps are specially designed to maintain a constant volumetric flow rate. As the air passes through the collection medium, usually a form of filter paper, particulate matter is deposited onto the filter in either a rectangular or circular pattern, depending on the instrument's design, and then the air continues on its way out of the monitor. The entire deposition area, regardless of its geometric shape, is assumed to be viewed by a radiation detector of a type appropriate for the nuclide in question. Moving filter monitors are often used in applications where loading of the filter medium with dust is an issue. This dust loading reduces the airflow over time. The moving filter collection medium, tape, is assumed to move across the deposition area at a constant, known rate. This rate is often established in such a way that a roll of the filter tape will last about 1 month. A typical filter movement rate is about 1 inch per hour. The rectangular window moving filter monitor will be denoted as RW, and the circular, CW fixed filter is FF. CPAMs are used to monitor the air effluents from nuclear facilities, notably power reactors. Here the objective is to assess the amount of certain radionuclides released from the facility. Real-time measurement of the very low concentrations released by these facilities is difficult. A more reliable measurement of the total radioactivity released over some time interval, days, perhaps weeks, may in some cases be an acceptable approach. In effluent monitoring, a sample of the air in the plant stack is withdrawn and pulled, down to the CPAM location. This sampled air in many cases must travel a considerable distance through piping. Extracting and transporting the particulates for the CPAM to measure in such a way that the measurement is representative of what is being released from the facility is challenging. In the USA, there are effluent monitoring requirements in both 10 CFR 20 and 10 CFR 50. Appendix B to the former and Appendix I to the latter are especially important. 10 CFR 50 Appendix A states: Criterion 64 Monitoring radioactivity releases. Means shall be provided for monitoring the reactor containment atmosphere, spaces containing components for recirculation of loss of coolant accident fluids, effluent discharge paths, and the plant environs for radioactivity that may be released from normal operations, including anticipated operational occurrences, and from postulated accidents. Also in the USA, Regulatory Guide 1.21, Measuring, Evaluating, and Reporting Radioactivity in Solid Wastes and Releases of Radioactive Materials and Liquid and Gaseous Effluents from Light Water-Cooled Nuclear Power Plants is highly relevant to the CPAM application. For occupational exposure, inhalation, assessment, CPAMs may be used to monitor the air in some volume, such as a compartment in a nuclear facility where personnel are working. A difficulty with this is that, unless the air in the compartment is uniformly mixed, the measurement made at the monitor location may not be representative of the concentration of radioactive material in the air that the workers are breathing. For this application, the CPAM may be physically placed directly in the occupied compartment, or it may extract sampled air from the HVAC system that serves the compartment. The following portions of 10 CFR 20 are relevant to the requirement for occupational exposure CPAM applications in the USA. 10 CFR 20.1003, Definition of Airborne Radioactivity Area, 1201, 1204, 1501, 1502, 2103. Radiation monitors in general have a number of process control applications in nuclear power plants. A major CPAM application in this area is the monitoring of the air intake for the plant control room. In the event of an accident, high levels of airborne radioactivity could be brought into the control room by its HVAC system. The CPAM monitors this air and is intended to detect high concentrations of radioactivity and shut down the HVAC flow when necessary. For use in the USA, Standard 10 CFR 50 Appendix A states: Criterion 19 Control Room. A control room shall be provided from which actions can be taken to operate the nuclear power unit safely under normal conditions and to maintain it in a safe condition under accident conditions, including loss of coolant accidents. Adequate radiation protection shall be provided to permit access and occupancy of the control room under accident conditions without personnel receiving radiation exposures in excess of 5 rem whole body, or its equivalent to any part of the body, for the duration of the accident. Equipment at appropriate locations outside the control room shall be provided. 1. With a design capability for prompt hot shutdown of the reactor, including necessary instrumentation and controls to maintain the unit in a safe condition during hot shutdown, and 2. With a potential capability for subsequent cold shutdown of the reactor through the use of suitable procedures. This defines a requirement for monitoring the air intake for the control room, such that the exposure limits, including for inhalation exposure, shall not be exceeded. CPAMs are often used for this. Leakage from the so-called reactor coolant pressure boundary is required to be monitored in USA nuclear power plants. Monitoring the airborne particulate radioactivity in the reactor containment structure is an acceptable method to meet this requirement, and so CPAMs are used. It is the case that when primary coolant escapes into the containment structure, certain noble gas nuclides become airborne and subsequently decay into particulate nuclides. One of the most common of these pairs is 88Kr and 88Rb. The latter is detected by the CPAM. Relating the observed CPAM response to the 88Rb back to a leakage rate from the primary system is far from trivial. The regulatory basis for the CPAM application is found in 10 CFR 50 for use in the USA, Standard 10 CFR 50, Appendix A, General Design Criteria for Nuclear Power Plants, Criterion 30, Quality of Reactor Coolant Pressure Boundary, requires that means be provided for detecting and, to the extent practical, identifying the location of the source of reactor coolant leakage. The specific attributes of the reactor coolant leakage detection systems are outlined in Regulatory Positions 1 through 9 of Regulatory Guide 1.45. For use in the USA, Standard 10 CFR 50.36, Technical Specifications, Paragraph C. 2. 2. A. specifies that a limiting condition for operation be established for installed instrumentation that is used to detect and indicate in the control room a significant abnormal degradation of the reactor coolant pressure boundary. This instrumentation is required by specification March 4, 15, RCS leakage detection instrumentation. Step changes in reactor coolant leakage can be detected with moving filter media to satisfy the quantitative requirements of US NRC Regulatory Guide 1.45. See description for US Patent Number 534-3046, 1994. The mathematical method is highly detailed and it focuses on time-dependent viewable collected activity, rather than concentration, as F.T. The method, among other features, yields the desired fixed filter to generate case filter paper velocity equals 0. The method was first put into use in the 1990s at a nuclear power plant in the United States. Though originally derived for dominant KR88/RB88 and leaked reactor coolant, it has been expanded to include CA138/CS138 and can be modified by replication to include any and similar pairings. Further refinements to mathematical methodologies have been made by the inventor. These set aside the patented collimator apparatus for making the quantitative assessment of leak rate step change when rectangular or circular collection grids are employed. The new methods are the simplest obtainable and are appropriate for any array of input concentrations. The response of the monitor is sensitive to the half-life of the nuclide being collected and measured. It is useful to define a long-lived LL nuclide to have negligible decay during the measurement interval. On the other hand, if the decay cannot be ignored, the nuclide is considered short-lived, SL. In general, for the monitor response models discussed below, the LL response can be obtained from the SL response by taking limits of the SL equation as the decay constant approaches 0. If there is any question about which response model to use, the SL expressions will always apply. However, the LL equations are considerably simpler and so should be used when there is no question about the half-life. Example 137 CS is LL. The output of the radiation detector is a random sequence of pulses, usually processed by some form of rate meter, which continuously estimates the rate at which the detector is responding to the radioactivity deposited on the filter medium. There are two fundamental types of rate meters, analog and digital. The rate meter output is called the count rate, and it varies with time. Rate meters of both types have the additional function of smoothing the output count rate estimate, i.e., reducing its variability. This process is more correctly termed filtering. Rate meters must make a trade-off between this necessary variance reduction and their response time. A smooth output, small variance, will tend to lag behind an increase in the true pulse rate. The significance of this lag depends on the application of the monitor. Even when the filter medium is clean, that is, before the pump is started that pulls the air through the filter, the detector will respond to the ambient background radiation in the vicinity of the monitor. The count rate that results from deposited radioactivity is called the net count rate, and is obtained by subtracting this background count rate from the dynamically varying count rate that is observed once the pump is started. The background is usually assumed to be constant. The count rate of the monitor varies dynamically, so that a measurement time interval must be specified. Also, these are integrating devices, meaning that some finite time is required to accumulate radioactivity onto the filter medium. The input to the monitor is, in general, a time-dependent concentration in air of the specified nuclide. However, for the calculations given below, this concentration will be held constant over that interval. Since concentrations resulting from physical events tend to vary with time, due to dilution processes and/or a non-constant source term, airborne radioactivity emission rate, it is not realistic to hold the concentration constant for significant lengths of time. Thus, measurement intervals on the order of several hours are not plausible for the purposes of these calculations. There are situations in which a nuclide deposited on the CPAM filter decays into another nuclide, and that second nuclide remains on the filter. This parent progeny or decay chain situation is especially relevant to so-called radon-4on, RNTN, or natural airborne radioactivity. The mathematical treatment described in this article does not consider this situation, but it can be treated using matrix methods, see Ref 11. Another issue is the fact that in a power reactor context it would be unusual for a CPAM to be collecting only a single particulate nuclide. More likely there would be a mixture of fission product and activation product nuclides. The modeling discussed in this article considers only one nuclide at a time. However, since the radiation emitted by each nuclide is independent of the others, so that the nuclides present on the filter medium do not interact with each other, the monitor response is the linear combination of the individual responses. Thus, the overall CPAM response to a mixture is just the superposition, i.e., the sum of the individual responses. CPAMs use either a Geiger tube for gross beta gamma counting or a NiTl crystal, often for simple single-channel gamma spectroscopy. In this context, gross means a measurement that does not attempt to find the specific nuclides in the sample. Plastic scintillators are also popular. Essentially, in power reactor applications, beta and gamma are the radiations of interest for particulate monitoring. In other fuel cycle applications, such as nuclear reprocessing, alpha detection is of interest. In those cases, the interference from other isotopes such as RNTN is a major problem, and more sophisticated analysis, such as the use of HPGO detectors and multi-channel analyzers, are used where spectral information, such as is used for radon compensation, is required. Radioiodine, especially 131I, monitoring is often done using a particulate monitor setup, but with an activated charcoal collection medium, which can absorb some iodine vapors as well as particulate forms. Single-channel spectroscopy is usually specified for iodine monitors. Detailed mathematical models that describe the dynamic, time-dependent count rate response of these monitors in a very general manner are presented and will not be repeated here. For the purpose of this article, a few useful results from that paper will be summarized. The objective is to predict the net count rate of a CPAM for a single, specific man-made nuclide, for a given set of conditions. That predicted response can be compared to the expected background and/or interferences, nuclides other than the one sought, to assess the monitor's detection capability. The response predictions can also be used to calculate alarm setpoints that correspond to appropriate limits, such as those in 10 CFR 20, on the concentration of airborne radioactivity in the sampled air. The parameters used in these models are summarized in this list. Time interval, T, time, measured from start of concentration step. Concentration, Q0, activity/volume, assumed constant over the interval. Decay constant, lambda, 1/time, for the specified nuclide. Media collection/retention efficiency, 5, implicitly includes line loss. Window length or radius, L or R, length, consistent units with V. Filter speed, V, length/time, length has same units as L or R. Flow rate, Fm, volume/time, assumed constant over the interval. Detection efficiency, epsilon, counts/disintegration, implicitly includes emission abundance. Line loss refers to the losses of particulate matter in transit from a sampling point to the monitor, thus the concentration measured would be somewhat lower than that in the original sampled air. This factor is meant to compensate for these losses. Sampling lines are specifically designed to minimize these losses, for example, by making bends gradual as opposed to right-angled. These lines, pipes, are needed since in many applications the CPAM cannot be physically located directly in the sampled air volume, such as a nuclear power plant's main stack, or the ventilation air intake for the plant control room. Emission abundance refers to the fact that the disintegration of any given nucleus of the isotope of interest in the CPAM analysis may not result in the emission of the radiation being detected, example a beta particle or gamma ray. Thus, overall there will be some fraction of the disintegrations that emit the radiation of interest, e.g. the 662 keV gamma ray of 137 CS is emitted in about 85% of the disintegrations of 137 CS nuclei. The response models are based on the consideration of the sources and losses of the deposited radioactivity on the filter medium. Taking the simplest case, the FF monitor, this leads to a differential equation which expresses the rate of change of the monitor count rate. The C F F the T equals epsilon K F M Q T lambda C F F \display style D \dot C underscore FF \over DT comma comma equals comma var epsilon K F underscore N comma phi Q T backslash comma backslash comma dash backslash comma backslash comma backslash lambda backslash comma backslash dot c underscore ff. The first term accounts for the source of radioactivity from the sampled air, and the second term is the loss due to the decay of that radioactivity. A convenient way to express the solution to this equation uses the scalar convolution integral, which results in C F F T equals epsilon K F M exp lambda T indefinite integral 0 T Q tau exp lambda tau the tau plus C 0 exp lambda T backslash display style backslash dot C underscore ff T backslash comma equals backslash comma backslash var epsilon backslash K backslash F underscore and backslash 5 backslash comma backslash exp backslash left dash backslash lambda backslash T backslash right backslash comma backslash int underscore 0 caret TQ backslash out backslash comma backslash exp backslash lambda backslash doubt backslash d backslash tau backslash comma plus backslash dot c underscore 0 backslash exp backslash left dash backslash lambda backslash t backslash right. The last term accounts for any initial activity on the filter medium and is usually set to 0, clean filter at time 0. The initial count rate of the monitor, before the concentration transient begins, is only that due to ambient background. If radon progeny are present, they are assumed to be at equilibrium in generating a constant count rate that adds to the ambient background's count rate. Various solutions for the time-dependent FF count rate follow directly, once a concentration time-dependence Q, T, has been specified. Note that the monitor flow rate Fm is assumed constant. If it isn't, and its time dependence is known, then that Fn, T, would need to be placed inside the integral. Also note that the time variable in all the models is measured from the instant the concentration in the sampled air begins to increase. For the moving filter CPAMs, the above expression is a starting point, but the models are considerably more complicated, due to 1. The loss of material as the filter medium moves away from the detector's field of view and 2. The differing lengths of time that parts of the filter medium have been exposed to the sampled air. The basic modeling approach is to break down the deposition regions into small differential areas and then consider how long each such area receives radioactive material from the air. The resulting expressions are integrated across the deposition region to find the overall response. The RW solution consists of 2 double integrals, while the CW response solution consists of 3 triple integrals. A very important consideration in these models is the transit time, which is the time required for a differential area to traverse the window along its longest dimension. As a practical matter, the transit time is the time required for all differential elements that were in the deposition window at time 0 to leave the window. This figure shows contours of constant activity on a CW deposition area after the transit time has expired. The filter moves from left to right, and the activity increases from left to right. The differential areas on the diameter have been in the deposition window the longest, and at the far right, have been in the window, accumulating activity, for the full transit time. Finally, to illustrate the complexity of these models, the RW response for time less than the transit time is C R W T equals epsilon K F M exp lambda T L indefinite integral 0 V T indefinite integral T X V T Q tau exp lambda tau the tau the X plus indefinite integral V T L indefinite integral 0 T Q tau exp lambda tau the X backslash display style backslash dot C underscore RW T backslash comma equals backslash var epsilon backslash K backslash F underscore and backslash 5 backslash exp backslash left dash backslash lambda backslash T backslash right backslash over L backslash left backslash int underscore 0 caret V backslash T backslash int underscore T backslash comma dash backslash left X backslash over V backslash right caret TQ backslash town backslash exp backslash lambda backslash comma backslash town backslash D backslash tau backslash DX backslash comma plus backslash backslash int underscore V backslash T caret L backslash int underscore 0 caret TQ backslash doubt backslash exp backslash lambda backslash tau backslash D backslash tau backslash DX backslash right. And, also, one of the CW triple integrals is superimposed on the contour plot. In these equations, K is a conversion constant for units reconciliation. Again, a very important parameter for moving filter monitors is the transit time, T, which is the window length, or diameter, divided by the filter tape speed V. The count rate is denoted by C backslash display style backslash dot C F T equals epsilon K F M Q 0 1 exp lambda T lambda backslash display style backslash dot C underscore FF T equals backslash var epsilon backslash K backslash F underscore and backslash 5 backslash Q underscore 0 1 backslash dash backslash exp dash backslash lambda backslash T backslash over backslash lambda C F T equals epsilon K F M Q 0 T backslash display style backslash dot C underscore FF T equals backslash var epsilon backslash K backslash F underscore and backslash 5 backslash Q underscore 0 backslash T C R W T equals epsilon K F M Q 0 lambda 2 V L lambda T 1 plus exp lambda T plus epsilon K F M Q 0 lambda 1 V T L 1 exp lambda T backslash display style backslash dot C underscore RW T backslash equals backslash var epsilon backslash K backslash F underscore and backslash 5 backslash Q underscore 0 backslash over backslash lambda caret 2V backslash over L backslash left backslash lambda backslash T backslash dash backslash 1 backslash plus backslash exp dash backslash lambda backslash T backslash right backslash plus backslash var epsilon backslash K backslash F underscore and backslash 5 backslash Q underscore 0 backslash over backslash lambda backslash left 1 dash V backslash T backslash over L backslash right backslash left 1 backslash dash backslash exp dash backslash lambda backslash T backslash right C R W T equals epsilon K F M Q 0 T V T 2 L backslash display style backslash dot C underscore RW T backslash comma backslash comma backslash comma equals backslash comma backslash comma backslash comma backslash var epsilon backslash k backslash f underscore n backslash comma backslash phi backslash q underscore 0 backslash left t backslash comma dash backslash comma v backslash t caret 2 backslash over 2l backslash right. Note that as v approaches 0, these RW equations reduce to the FF solutions. C R W T equals epsilon K F M Q 0 1 lambda V lambda 2 L 1 exp lambda L V backslash display style backslash dot c underscore rw t backslash comma equals backslash comma backslash var epsilon backslash k backslash f underscore n backslash comma phi backslash q underscore 0 backslash comma backslash left backslash 1 backslash over backslash lambda backslash comma dash backslash comma v backslash over backslash lambda caret 2l backslash left 1 backslash comma dash backslash comma exp backslash left dash backslash lambda and l backslash over v backslash right backslash comma right backslash c r w t equals epsilon k f m q 0 l 2 v backslash display style backslash dot c underscore rw t backslash comma equals backslash comma var epsilon backslash k backslash f underscore n backslash comma phi backslash q underscore 0 backslash comma l backslash over 2 backslash v backslash comma. These response model equations are quite complicated and some involve a non-elementary integral. The exact solutions can be found here. It is shown here, however, that a reasonable approximation for predicting the CW response can be obtained by using the RW equations above, with an adjusted window length LCW used in each occurrence of the parameter L, except that the CW transit time TCW is found from 2R/V, not from using LCW as given here in the TRW relation L/V. Thus, L C W equals 16 R 3 pi t c w equals 2 r v is not equal to L c w v t r w equals L v backslash display style L underscore CW equals backslash comma 16 backslash R backslash over 3 backslash comma pi backslash comma 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 backslash T underscore CW backslash comma equals backslash comma 2 R backslash over V backslash comma backslash nick backslash comma L underscore CW backslash over V backslash comma backslash T underscore RW equals backslash comma L backslash over V. These plots show the predicted CPAM count rate responses for these parameter settings. Detection efficiency 0.2, flow rate 5 cubic feet per minute, CFM, collection efficiency 0.7, constant concentration 1 times 10 to the power of -9th. Mu backslash display style backslash moon CI/CC, rectangular window length 2 inches, circular window radius 1 inch, media tape speed 1 inch/hour. The concentration instantly steps up to its constant value when the time reaches 30 minutes, and there is a 100 count per minute, CPM, constant background. Note, a microcurie mu display style moon. Ci is a measure of the disintegration rate, or activity, of a radioactive source. It is 2.22 times 10 to the power of 6 disintegrations per minute. In the LL plot, note that the effect count rate continues to increase. This is because there is no significant loss of radioactivity from the filter medium. The RW and CW monitors, on the other hand, approach a limiting count rate and the monitor response remains constant as long as the input concentration remains constant. For the SL plot, all three monitor responses approach a constant level. For the FF monitor, this is due to the source and loss terms becoming equal. Since 88Rb has a half-life of about 18 minutes, the loss of radioactive material from the filter medium is significant. This loss also happens on the RW and CW monitors, but there, the loss due to the filter movement also plays a role. In both plots, Poisson noise is added and a constant gain digital filter is applied, emulating the count rate responses as they would be observed on a modern CPAM. The horizontal dotted lines are the limiting count rates calculated from the equations given in the previous section. Also in both plots the transit times are indicated. Note that these times are measured from the start of the concentration, at time 30 minutes, not from the arbitrary time 0 of the plots. In these example graphs, the length of the RW and the diameter of the CW are equal. If they were not equal, then the transit times would not be equal. Having mathematical models that can predict the CPAM response, i.e., the monitor's output, for a defined input, airborne radioactive material concentration, it is natural to ask whether the process can be inverted. That is, given an observed CPAM output, is it possible to estimate the input to the monitor? A number of approaches to this inverse problem are addressed in detail in. Each method has its advantages and disadvantages, as one might expect, and a method that might work well for a fixed filter monitor may be useless for a moving filter monitor, or vice versa. One important conclusion from this paper is that for all practical purposes moving filter monitors are not usable for quantitative estimation of a time-dependent concentration. The only moving filter method that has been used historically involves a constant concentration, LL assumption, which leads to the RW expression. C R W equals epsilon K F M Q 0 T 2 Q caret 0 equals 2 V C R W epsilon K F M L display style dot C underscore RW equals var epsilon K F underscore and 5 Q underscore 0 T over 2 right arrow hat Q underscore 0 equals 2 V dot C underscore RW over var epsilon K F underscore and 5 L. Or for CW. C W equals epsilon K F M Q 0 8 R 3 pi V Q caret 0 equals 3 pi V C W 8 R epsilon K F M display style dot C underscore CW equals var epsilon K F underscore and 5 Q underscore 0 8 R over 3 pi V right arrow had q underscore 0 backslash comma equals backslash comma 3 backslash pi backslash v backslash dot c underscore cw backslash over 8 r backslash var epsilon backslash k backslash f underscore n backslash phi. Thus, a concentration estimate is available only after the transit time t has expired. In most CPAM applications, this time is on the order of several, example 4, hours. Whether it is reasonable to assume that the concentration will stay constant for this length of time, and to further assume that only long-lived nuclides are present, is at least debatable, and it is arguable that in many practical situations these assumptions are not realistic. For example, in power reactor leak detection applications, as mentioned in the first section of this article, CPAMs are used, and a primary nuclide of interest is 88Rb, which is far from long-lived, half-life 18 minutes. Also, in the dynamic environment of a reactor containment building, the 88Rb concentration would not be expected to remain constant on a time scale of hours, as required by this measurement method. However, realistic or not, it has for decades been the practice of CPAM vendors to provide a set of curves, graphs, based on the expressions above. Such graphs have concentration on the vertical axis, and net count rate on the horizontal axis. There often is a family of curves, parameterized on the detection efficiency, or labeled as to specific nuclides. The implication in providing these graphs is that one is to observe a net count rate, at any time, enter the graph at this value, and read up the concentration that exists at that time. To the contrary, unless the time is greater than the transit time t, the nuclide of interest is long-lived, and the concentration is constant over the entire interval. This process will lead to incorrect concentration estimates. As discussed in the referenced paper, there are at least 11 possible quantitative methods for estimating the concentration or quantities derived from it. The concentration may only be at a specific time, or it might be an average over some time interval. This averaging is perfectly acceptable in some applications. In a few cases, the time-dependent concentration itself can be estimated. These various methods involve the count rate, the time derivative of the count rate, the time integral of the count rate, and various combinations of these. The count rate is, as mentioned above, developed from the raw detector pulses by either an analog or digital rate meter. The integrated counts are easily obtained simply by accumulating the pulses in a scaler or, in more modern implementations, in software. Estimating the rate of change, time derivative, of the count rate is difficult to do with any reasonable precision, but modern digital signal processing methods can be used to good effect. It turns out that it is very useful to find the time integral of the concentration, as opposed to estimating the time-dependent concentration itself. It is essential to consider this choice for any CPAM application. In many cases, the integrated concentration is not only more useful in a radiological protection sense, but is also more readily accomplished, since estimating a concentration in, more or less, real time is difficult. For example, the total activity released from a plant stack over a time interval. Eta /display_eta is R S T K C K eta equals indefinite integral 0 eta q tau f s t k c k tau the tau /display_r_stack_left /eta /right equals and underscore 0 caret /etaq /doubt /f_stack /doubt /d Then, for a fixed filter monitor, assuming a constant stack and monitor flow rate, it can be shown that R S T K C K eta equals F S T K C K C eta plus lambda indefinite integral 0 eta C tau the tau epsilon K F M /display_r_stack /left /eta /right backslash comma backslash comma backslash comma equals backslash comma backslash comma backslash comma F underscore stack backslash left backslash dot C backslash left backslash ETA backslash right backslash comma backslash comma backslash comma plus backslash comma backslash comma backslash comma backslash lambda backslash comma backslash and underscore 0 caret backslash ETA backslash dot C backslash left backslash tau backslash right backslash comma backslash D backslash tau backslash right backslash over backslash var epsilon backslash K backslash F underscore N backslash comma backslash phi. So that the release is a function of both the count rate and integrated counts. This approach was implemented at the SN1 nuclear power plant in the late 1960s for estimating the releases of episodic containment purges, with a predominant and strongly time-varying nuclide of 88 Rb. For a LL nuclide, the integral term vanishes, and the release depends only on the attained count rate. A similar equation applies for the occupational exposure situation, replacing the stack flow rate with a worker's breathing rate. An interesting subtlety to these calculations is that the time in the CPAM response equations is measured from the start of a concentration transient, so that some method of detecting the resulting change in a noisy count rate must be developed. Again, this is a good application for statistical signal processing that is made possible by the use of computing power in modern CPAMs. Which of these 11 methods to use for the applications discussed previously is not especially obvious, although there are some candidate methods that logically would be used in some applications and not in others. For example, the response time of a given CPAM quantitative method may be far too slow for some applications, and perfectly reasonable for others. The methods have varying sensitivities, detection capabilities, how small a concentration or quantity of radioactivity can reliably be detected, as well, and this must enter into the decision. The calibration of a CPAM usually includes 1. Choosing a quantitative method. 2. Estimating the parameters needed to implement that method, notably the detection efficiency for specified nuclides, as well as the sampling line loss and collection efficiency factors. 3. Estimating, under specified conditions, the background response of the instrument, which is needed for calculating the detection sensitivity. This sensitivity is often called the minimum detectable concentration or MDC, assuming that a concentration is the quantity estimated by the selected quantitative method. What is of interest for the MDC is the variability, not the level, of the CPAM background count rate. This variability is measured using the standard deviation. Care must be taken to account for bias in this estimate due to the autocorrelation of the sequential monitor readings. The autocorrelation bias can make the calculated MDC significantly smaller than is actually the case, which in turn makes the monitor appear to be capable of reliably detecting smaller concentrations than it in fact can. An uncertainty analysis for the estimated quantity, concentration, release, uptake, is also part of the calibration process. Other performance characteristics can be part of this process, such as estimating response time, estimating the effect of temperature changes on the monitor response, and so on. This is given to show context of US and SI units. Although the United States Nuclear Regulatory Commission permits the use of the units Curie, RAD, and REM alongside SI units, the European units of measurement directives require that their use for public health purposes be phased out by December 31, 1985. References